runway de la NASA, représentant. Venez, donc, bienvenue.
Merci.
Oui.
My French is not good enough to give this speech in French, so I will speak in English, but I'm sure that you will understand. So, today I will speak about a different way to study what's outside the Earth atmosphere. So, the first celestial body that we have is our natural satellite, the Moon. And I will talk about this technique that we are using in Matera, where there is the Italian Space Geodesy Center, to study the Moon, but also to study, as we will see, something very fundamental and something related to the Einstein theory of gravity. So, let's start from the Apollo 11 mission. I think that most of you are very familiar with this fantastic enterprise who allowed mankind to step foot on the Moon for the first time. But maybe not all of you knows that after leaving, the American astronaut left several scientific instruments, and one of them is actually still working today. And it's this object here that after 50 years is still getting us useful information. And it is a panel of retroreflectors, very similar to those that you have on your bicycle, let's say. And these are just 3 mirrors arranged as a corner cube. So it has the optical property to back reflect the light from whichever is the incoming direction. So if the light is coming from upward, it will reflect upward. If the light is coming from downward, it will reflect the light downward. But Apollo 11 is not the only mission who left some retroreflectors on the Moon. And as you can see, there are also the mission Apollo 14 and 15. This is the map of the Moon where all the retroreflectors are today present. And also the 2 Soviet rover, Luna Code 1 and Luna Code 2. To study, to exploit this retroreflector, there is also a network of ground stations, and one is in Grasse. Actually, this is the most proficient of all the network. And another one is in Italy, in Madeira. But of course, there are a lot of them around the world. Well, actually, not so many, but still, they cover more or less all the world. So, which is the principle? Why do we use, what do we need the retroreflectors? Well, the idea is to use them for space telemetry, let's say lunar laser ranging. And the principle is simple. We shine a small laser pulse toward the Moon. This laser pulse hits the retroreflector, get back reflected on the Earth, and we can measure precisely the time it took from the light to go from the Earth to the Moon and back. By measuring the time of flight, it is possible to measure the distance from the Earth of the Moon, because, as you know, light travels at the speed of light, and which is a known constant. And so, at the end of the day, what we do with the lunar laser ranging is make a very precise measurement of the distance from the Earth to the Moon. And I'm talking about a few centimeters over more than 300,000 kilometers. But why is it so difficult to do that? Why there are so few stations that can actually do lunar laser ranging? It's because we have a huge attenuation. In fact, if you are sending something like 10 to the 17 photon for each light pulse, is one with the 17 zero afterward, we only get 0.01 photon per pulse. So we lose most of them. Actually, yes, we have very, very little tiny signal. So one can ask if it's really worth it to do all this experiment to have this few photon that tells us the precise distance. What we can do with this measurement, with the knowledge of the distance between the Earth and the Moon, is, well, there are many things that we can do, and one of them is to test the equivalence principle. So, the equivalence principle, probably some of you are already familiar with that, maybe most of you, but I will just explain you quickly. Well, on the left side, you see Homer Simpson, which is on the weight scale, and you know that if Homer Simpson starts eating donuts, he will become fatter and fatter, and he will read a higher number. Why is that so? Because he is increasing his gravitational mass, so the Earth is attracting him with a stronger force. On the other side, we have this guy here, this gentleman who is, with his body is moving a whole airplane, a Boeing 701. And what he tells us is that this is the worst Guinness record for the most strength man on Earth. And what it can tell us is if an object is big, so it has a high mass, it's very difficult to move it, actually also to stop it. It's very difficult to make it change velocity. This is because of its inertia. So here we have a concept of mass that is gravitational, so the more massive an object is, the more is attracted down toward the Earth. And here we have another concept of mass, the inertia. Now, it turns out that these two masses actually have the same value, and this equivalence principle is at the basis of the, well, several theories of gravity, but the most important is Einstein general relativity. And how can we test this equivalent principle? How can we test this fact that the two masses are actually the same, have the same experimental value? Well, one idea is the free fall of object. So we take two objects, one very heavy, like a hammer, and one very light, like as a feather, and we'll drop them. So what happens is that the hammer, which has a higher mass, has a higher gravitational mass, so it will experience a stronger force. So it will be pulled with a stronger force down to the Earth. But it will also have a higher inertial mass, as this gentleman here can tell us. So it will try to not to change the velocity, let's say. It will try to obstacle its movement. If these two masses are equal, and the same happens for the feather, which is lighter, so it has a lighter force, but also a lighter inertia. But if the two masses are the same, then the two objects will fall with the same acceleration. This experiment has been done on the Moon and in the Apollo 7. Well, it has been repeated several times, but one time also on the Moon by the Apollo 17 mission, and I will show you the experiment. Okay, so this is a very simple experiment. By principle, you just let two twin drop. And what we saw is that the feather and the hammer have different masses, but they experience the same acceleration. And as the Moon attracts both the feather and the hammer, likewise the Sun attracts both the Moon and the Earth. So if the two masses, gravitational and inertial mass, are the same, they should experience the same acceleration. So with lunar laser ranging, it is possible to monitor very precisely the orbit of these two objects, celestial body, the Earth and the Moon, and to actually establish a bound on the difference between the inertial and gravitational mass. And we can measure very precisely that these two masses are equal, down to 10 to the minus 13 level, which is quite good. And well, if I have just last slide, there are other things that we can do with the lunar laser ranging is that studying the motion of the moon, and by that we can deepen our understanding of what's inside the moon. In fact, by lunar measurement, lunar laser ranging measurement, it has been possible to discover that the moon has a fluid interior, at least part of that is molten. And it is also used to study, to have a better understanding of the Earth and of its center of mass. It's running out, so I stop here. Okay, thank you.
Merci beaucoup. Alors, dans l'ordre, on est